In Lesson 24, I said that I think there are 4 classes of surface forces. I spoke about 3 of them. Here in Lesson 25, it's time to talk about the 4th class, electrodynamic. As the name implies, charges are moving. Those give rise to fluctuating electric fields, which in turn generate force. You might have already heard the name van der Waals. Van der Waals was a very determined Dutch physicist. In his day, being the son of a carpenter, working class people, he did not receive training in the classical languages of Latin and Greek. This meant that he was not qualified to be a regular student at university. But the times changed, and the Minister of Education gave him special permission to do a PhD in physics, and he defended his dissertation in 1873. He went on to do important work, which was recognized by the Nobel Prize in Physics in 1910. In Lesson 24, I spoke a little bit about dipoles. The dipoles are essential to Lesson 25, so I think it's worth it to review them. If we have a positive charge and a negative charge of equal magnitude, and they're separated by a distance, that configuration of charge is known as a dipole. We represent it by an arrow with the tip pointing in the positive direction. It turns out that there are both permanent and temporary dipoles. An example of a permanent dipole is the water molecule. The water molecule has 2 hydrogen atoms and 1 oxygen atom, and instead of being in a line, they're in a configuration like this. The oxygen is electronegative, which means it grabs electrons, which means this side of the oxygen is more negative. The electrons from the hydrogen atoms have shifted down towards the oxygen, leaving the nuclei, the protons of the hydrogen atoms more exposed. So the water molecule then has positive and negative ends, and therefore it is a permanent dipole. As far as temporary dipoles are concerned, an example would be the atom of neon. So it has a positive nucleus, and you can think of the electrons roaming around it as like a cloud of electrons. When there's no electric field acting on the neon, then that electron cloud is symmetric and centered on the neon nucleus. But if you put it in an electric field, what happens is that the electron cloud sort of shifts down away from the electric field, and then now we've got a dipole like this, with the nucleus positive, the electron cloud negative, and so it's as if we have extra positive charge right at the nucleus and negative charge in the cloud. Now, when you take the electric field away, then the atom returns to its state above, where there's no dipole, and so this is a temporary dipole. When we say that the atom is polarizable. Here are the 3 types of interactions that are the origins of van der Waals forces. So if we have polarizable molecules, or atoms, as all atoms are, in fact, then as the electrons around them fluctuate back and forth, which is something they naturally do at frequencies of 10 to the 14th times per second, then we would draw dipoles like this. And that would be their natural configuration. This is the lowest energy state of dipoles, is to be pointing in the opposite directions, because the positive ends attract the negative ends, and vice versa. We also have rotating permanent dipoles, such as two water molecules. If they can flip back and forth, they don't do that at 10 to the 14th times per second, but nonetheless, water molecules do jostle around, and the dipoles change orientation. Again, I've drawn the preferred orientation, but thermal energy keeps them moving, and the electric fields fluctuating. And then we have the third class, where a permanent dipole is interacting with a polarizable atom, i.e. a temporary dipole. And in this case, the permanent dipole need not be in fluid. It could be fixed as well as rotating, and that polarizable atom could, of course, be anywhere. Next, we'll look at how these dipoles lead to force. Let's look at the forces between two dipoles, starting with the positive charge in the upper left. It will be repelled from the positive charge in the lower right and attracted to the negative charge in the upper right. Similarly, for the negative charge in the lower left, it will be repelled from the negative charge in the upper right and attracted to the positive charge in the lower right. Note that the vectors I drew representing force, the horizontal ones are a little bit longer than the ones pointed at angles, because those charges are slightly closer than the charges that are across the corners. If I now break the forces that are at an angle into components, horizontal and vertical, that looks like this, and I'm doing a vector sum now, and the vertical components cancel each other. The horizontal components take away a little bit of the magnitude of the right-pointing vectors, but overall you get a net force by a graphical sum of all those vectors that looks like this. So the dipole on the left is attracted to the dipole on the right. If you do the same thing for the dipole on the right, because due to the forces acting on it from the dipole on the left, you end up with this situation. A force equal in magnitude and opposite in direction. You might remember from introductory physics that a dipole puts out an electric field that is proportional to the distance away from it, inverse cubed, and something like this, and electric field lines point in the direction that a positive charge would move. So electric field is proportional to 1 over r cubed, and forces are equal to charge times electric field. And if these dipoles we've been speaking about are polarizable, which they all are, then the amount of charge that is polarized is also dependent on the electric field. So the force then from a single interaction is proportional to 1 over r to the 6. And then when you sum forces, for example, the 4 red vectors there, it turns out that that is proportional to 1 over r to the 7th. And from that, you can get the attractive potential between two dipoles. And so that is proportional to the separation to the sixth power, to the minus sixth power. Why is that important? It's important because there's something called the Leonard Jones potential that's quite common, something you should know about. I've sketched it here. Potential is a function of separation r, and you see that there's a very familiar looking dip with a minimum at position r0 with a depth of u0. That should be minus u0. The equation for this is that potential, Leonard Jones potential as a function of r, is equal to u0 quantity r0 over r to the 12th power minus 2 r0 over r to the 6th power. Now, this inverse 6th power is what we've just been talking about, a dipole-dipole interaction. That r inverse r to the 12th power, that is repulsion, where the electron clouds of the dipoles are starting to overlap. That's what's dominating up here. The inverse 6th power is active down there, and here is where both terms are important. This is a very familiar shape. This is the same kind of shape as I've been drawing in force curves, but yet it is a very different functional dependence. We're not talking about r to the 6th and r to the 12th when we're doing force curve acquisition. So what's the relationship here? Starting with potential between two dipoles, we can get the potential between a tip and a sample because we can integrate over the volume. We can say, let's pretend we have a dipole near a semi-infinite half-space and integrate up all the dipoles in that semi-infinite half-space with respect to how far away that dipole is from the surface. That potential becomes 1 over distance cubed, because you're integrating over the 3 dimensions of the volume. And then, knowing that, you integrate up over the hemisphere of the tip, and you get 1 over distance, and you know that force is the negative derivative of potential. And so, eventually, we know that force between a hemispherical tip and the sample surface should go as an attraction and the inverse distance squared. One of the assumptions in this calculation is that the tip radius is much, much bigger than the separation, which is always true in a surface forces apparatus, but not necessarily true for atomic force microscopy. Here's the result. The van der Waals force is equal to minus 2 pi times the tip radius times the work of adhesion times the quantity delta 0 over delta squared, where delta 0 is an interatomic distance, that is the separation at contact. I think it's cool that with an AFM you can measure intermolecular dipole-dipole attractions just due to rotating atoms or fluctuations of electrons.